So chapter 3, as you remember, in the previous lecture, we said we have conservation of mass principle. So this conservation of mass says the total mass cannot be created, cannot be destroyed. Okay. So if you have closed system, the total mass in the system must be constant. And we have two examples to demonstrate how we can use this conservation of mass principle in order to solve the problems, analyze different problems, find time that we have the faucet to be overflow, find the volume from one state to another state if we change temperature and pressure for these conditions. In order to understand the conservation of energy or the first law of thermodynamics, we can start with this example. Let's assume we have a ball, and I tell you this ball is resting at the floor, so the elevation from the floor, my reference, is 0. And this ball will start to move with a velocity of 5 meters per second. So this ball has this condition. If I ask you what is the summation of the potential and kinetic energy for this one, so what you should do, and they said, so kinetic energy plus potential energy, kinetic energy is half mv squared, potential energy is mgh, mgz. Substitute the numbers we have, and then the summation of total and potential energy for the ball at this position with this velocity is 0.025 kilojoule. Then I tell you, okay, this ball start to move. Now this ball is at elevation 1 meter from the ground, but the velocity change, it's 2.33 meters per second. What is the summation of potential and kinetic energy? Again, calculate potential and kinetic energy, and you can see the calculations on the top side. Third position, velocity is 0 meter per second, elevation 1.27. So the elevation change, the velocity change, what is the summation of potential and kinetic energy this ball has? So you can make the calculation, and this is the summation. Fourth position, different height, different velocity, summation of potential and kinetic energy, and also you can make the calculation. The common thing that we have in all of these calculations, that the summation of two potential energy and kinetic energy, regardless of the position, regardless of the velocity we have, it will be the same. And this is the conservation of energy principle. So we can have different positions, we can have different velocities, but if you want to analyze the amount of energy this system has, the total amount of energy should be what? Should be constant. So this is the first law of thermodynamics, which is conservation of energy. So it says energy is a conserved quantity. Energy cannot be created. Energy cannot be destroyed. Energy just can change from one form to another one. But if you calculate the total energy for the system, it will be constant. Clear? So this is the conservation of energy, or this is called the first law of thermodynamics that quantify for the energy content of a system that we have. So this is the definition, okay, the description of the first law of thermodynamics. Let's go to math. In math, how I can represent this principle or this law. Similar to conservation of mass, accumulation is in minus out. Okay, so what is the accumulation term? Accumulation, this is the rate of the change of total energy of the system. So if you have energy, focus on the energy content in the system and see how this energy content is changing with respect to time. Rate of energy change for the system. And if you remember from chapter 1, the energy stored in the system, which we define as static forms of energy. You remember it? How many static forms of energy we have? 3. Internal energy, kinetic, and potential. Okay, so the total energy of the system is summation of internal, kinetic, potential. Again, if you remember the last slide we have in chapter 1, we compared the values of potential, kinetic, internal, and we figured out that the value of potential and kinetic is very small compared to the internal, so usually we neglect them, and we said the total amount of energy that for any system is the internal energy, almost or approximately the internal energy. Okay, so again, the accumulation term, this one describes how the internal energy for the system will change with respect to time. So you can have it du by dt. If you have in a problem, you don't have internal energy, you have a specific internal energy, so it will be d by dt of mass times the specific internal energy. This term should be total internal energy, not specific, not molar. If in a problem you have molar internal energy, so multiply it with number of moles, because the overall or all this term should be du by dt. Okay, So you can represent this accumulation term by any one of this. So far is clear? Any questions? Okay. The right side, the input and output, these are two things, not one term. The first term is if you have inlets, if you have outlet, so the inlet or the energy content of the inlet stream, the energy content of the outlet stream should be accounted in this side. So this is the first, the first part that contributes to the inlet minus outlet. So if you have inlet stream, if you have outlet stream, any of these streams have value of internal energy, kinetic energy, potential energy, flow work. Okay? So all of these things, all of these four energy forms are accounted for each of the inlet and outlet streams in the right side of the equation. Okay, if we have closed system, so we don't have inlet, we don't have outlet, right? So does this mean that the right side of this energy equation will be zero? No, because this right side also accounts for another thing, which is the dynamic form of energy. Dynamic form of energy, the energy that can cross the boundary between system and surrounding, which is heat and work. So we have two things are contributed or should be considered when we calculate the right side of the equation. The first one is inlet and outlet, the energy content of any inlet stream, any outlet stream. And for the inlet and outlet, we have four terms we will consider: internal, kinetic, potential, flow work. If we have closed system, no inlet, no outlet, so still the right side of the equation will be there, because for closed system, energy, we have dynamic energy, can cross the boundary between system and surrounding, which is heat and work, and this also considered in the right side of the equation. Clear? Okay, let's put all of these things in the equation here. So we have the accumulation term. So we have here the accumulation term, which is du by dt, or d by dt of mass times specific internal energy. So this is the accumulation term. Equal inlets. So if you have inlet stream, if you have multiple inlet streams, so get the summation of all of these inlet streams. And we said we are considering internal energy, kinetic energy, potential energy from the inlet stream. Minus outlet, we are considering internal energy, kinetic energy, potential energy for the outlet streams. Plus work, plus Q. These two things are the dynamic forms of energy. So far is clear? Okay. We are missing one thing here. If you remember, let's get back to this slide. Here we said for the inlets and outlet streams, we have four terms we should consider, right? Internal, kinetic, potential, flow work, correct? Here, if we get back to this equation again, for the inlet and outlet, how many terms we are considering? Three: internal, potential, kinetic. So we are missing flow work, right? This term will not appear with the inlet and outlet, but this doesn't mean it will not be considered. It will be considered, but it will be considered with the work term. Okay, because if you remember the work term, we have three work categories. We have the first one, shaft work. The second one, work of expansion and contraction. And then we have this one, the flow work. So if we put it in full detail, so for the inlet and outlets, we have internal energy, we have kinetic energy, we have potential energy, and we have the flow work for the inlet and outlet. So now everything we mentioned in the previous slide is expressed in this mathematical equation. So far is clear? Any questions? Any doubts? Anyone cannot follow the math behind this equation?
So since this is accumulation of energy and all that, would isolation systems be just equal to zero since there's no...
Yeah. Because no heat, no mass can be considered. So this is a special case that's for this equation. Any questions? Just take your time if you need to write any notes. So again, this is the general form of the energy balance equation. This one can be applied for open system, can be applied for closed system. Okay, any one of them. So now let's see some special cases. If we have closed system. So in closed system, we have this PV term, this flow work will be neglected, right? Because we don't have inlet or outlet. Plus the inlet side term and the outlet term also will be neglected. So if you have closed system, this will be the form of the energy equation that you are using. There is no term for the inlet stream, no term for the outlet stream. Even in the work like term here, we don't have this flow work. So it will be the accumulation, du pi dt, equal work of expansion contraction, shaft work plus Q. Any heat can cross the system. There is nothing to repeat here to represent the inlet or the outlet. Make sense? Clear? Okay. If we have open system, let's get back to this one. So now, as we said, this flow work is for closed system, but now if we have open system, so this term will exist. And if you remember, we have U, this U is internal energy. If you remember chapter 2, we said the internal energy plus flow work, we can replace these two like properties or these two terms with a single term. Do you remember its name? Anyone remember? Internal energy plus flow work? Enthalpy. So internal energy plus flow work together, this is enthalpy. This is why when you analyze open systems, the term enthalpy start to appear instead of internal energy. Okay, so because we have here the because we have here the internal energy for the inlet and outlet, we have the flow work for the inlet and outlet, so you can combine both of them together to represent the enthalpy. And then the energy balance equation for the open system, this is how you represent it. So the left side, the accumulation, still the same, still internal energy, change of the internal energy with respect to time. But for the inlet and outlets, you have enthalpy instead of internal energy, you have kinetic energy, you have potential energy, and here you have work of expansion, contraction, shaft work plus Q. Flow work is embedded here in the enthalpy calculation. Okay, so this is the general form that we are using if you need to analyze any open system you have. So far it's clear? So now we understand what it means by the conservation of energy principle or the first law of thermodynamics. Then we explain the general form that we can use it to analyze open or closed system. Then we see the simplified one for the closed system and the simplified one for the open system. Clear? Okay. Let's have this one. If you have open system, so this is the equation we have. So again, the accumulation term, the left side of the equation. This accumulation term represents the energy content of the system and how will it change with respect to time. If you have any problem, and in this problem I told you, this process or this system operates or having any changes that happen at steady state, so this means the left side or the accumulation term is zero. So the left side, the accumulation will be zero if you have a steady state process. Steady state means any property you have in the system will be fixed or will be constant with respect to time. Clear? Okay. So this big term here we have, this is the inlet and this is the outlet. And again, these two terms neglected for closed systems. The first term in the inlet and the outlet, for this one, this is enthalpy. The second term here, this one and this one, this is kinetic energy of the inlet, kinetic energy of the outlet. These two terms, sometimes we can neglect them, remove them from the equation to simplify it. It's when, if you have the inlet velocity and the outlet velocity are equal. So if you have any problem, and in this problem you did the calculations, or you just see the problem statement and you can figure out that the inlet velocity and the outlet velocity are the same, so you can remove or neglect these terms from the equation. So this one can be removed from the equation in this case. Clear? So one other thing, I can tell you this. Based on the conservation of mass, we know that the total mass is constant, right? So if you have a problem, for example, and I tell you that I have pipe with constant cross section, and we have the total mass is constant in this one, and I ask you what will be the inlet velocity, what is the outlet velocity. So the inlet velocity and the outlet velocity here will be the same as long as the inlet diameter and the outlet diameter are the same. So if you have the diameter of this pipe at the inlet and diameter of this pipe at the outlet are the same, so this like gives you an idea that the velocity will be the same. Okay, so if diameter are the same, then velocity will be the same. If I have this case, for example, I have this pipe, or I have this inlet, or this system. This is the inlet. So this is velocity of the inlet, diameter of the inlet. This is the outlet, and the flow coming out from here. This is the velocity, and this is diameter at the outlet. So again, conservation of mass will tell you that total mass is constant. The same total mass coming in, the same total mass coming out. But here, the diameter are not constant, or are not the same. So if you notice this, so this means the velocity of the inlet doesn't equal the velocity of the outlet. And if you have this happen, so this term will exist. So far is clear? So you have inlet velocity, outlet velocity. These two terms can be cancelled if the inlet and outlet velocity are the same. Inlet out velocity can be the same if the inlet diameter and the outlet diameter is also the same. Any questions? Okay. This term, this one and this one represent the potential energy. If the inlet and outlet like at the same horizontal level, okay, so these two terms also will be cancelled. But if you have like inlet, for example, here. So if you have, this is your system. So we have here, this is the inlet, and here you have, this is the outlet. So this is the case where we have GH for the inlet, GH for the outlet cannot be like cancelled. But if you have, similar to this one, if you have pipe like this one here, so inlet and outlet at the same horizontal level, so remove this term from the equation. Remove potential energy for the inlet, potential energy for the outlet, they are the same. And here we have negative sign, so negative sign, these two terms automatically will be cancelled. Clear? Any questions? Okay. Then we have work of expansion contraction. This one usually occur for for closed system. This one you will have its value if you have like piston moving to cause expansion, to cause contraction. Shaft work, this one will exist if you have any like rotating machine. If you have problem, this problem has pump, fan, turbine, compressor, any rotating movement, so the shaft work will exist. But if you don't have any example of or any equipment that cause this rotating motion, so this term will be cancelled. And the last one is Q, the heat transfer between system and surrounding. This term is zero if the temperature of the system, temperature and surrounding are the same. Because they are the same, there is no temperature difference, there is no heat transfer. Or if I tell you in the problem that this process happen in adiabatic mode. Adiabatic means there is no heat transfer between system and surrounding. So if you see any of these two things, then you can neglect this term. If the process is adiabatic, or if you see that there is no changes in the temperature between system and surrounding. Okay? If you can understand like the meaning of each of these terms, then the analysis can be very easy. Clear? Let's take examples for this one. Here we have different examples. The principle, the first law of thermodynamics can be applied for nozzles, pumps, turbines, fans, heat exchangers, boilers. So a lot of chemical engineering, even environmental engineering applications, we can apply this one. Let's start with an example. So this example says we have steam. This steam flows through an adiabatic nozzle. Okay. So here we have this word, adiabatic. This adiabatic means which term will be cancelled? Q. So this one means Q is 0. So we have adiabatic nozzle. This adiabatic nozzle at steady state. This phrase, steady state, means which term will be 0? Accumulation term. Okay. Entering the nozzle with a pressure of 0.5 megapascal, temperature 400 degrees Celsius, exiting at 0.1 megapascal, 350 degrees Celsius. What is the exiting velocity? What is velocity at the outlet? Okay, so again, this system is open or closed system. So this is an open system. Okay, so let's say the conservation of energy for open system let's start with the general one. So we have the accumulation du by dt equal we have one inlet stream, so there is no submission. So mass flow rate of the inlet times specific enthalpy of the inlet plus velocity of the inlets over 2 plus g, the elevation of the inlet, minus mass flow rate of the outlet times specific enthalpy of the outlet plus outlet velocity over 2 plus g, gravity, times the elevation of the outlet, plus group of expansion contraction plus shaft work plus Q. This is the general form of the equation we have. So now let's see the terms. So this term, the accumulation term, will be 0, because he said that in this problem we have steady state condition. This term Q will be 0, because in the problem itself he said we have adiabatic. Okay. So now for this example, do you see any difference in the level between the inlet and outlet? Or it looks like they are almost at the same horizontal level? Almost they are on the same horizontal level. So this one, this term, will be cancelled with this one. So these are cancelled because inlets and outlets are at same horizontal level. Okay. Here, can you see any pump, any fan, any compressor, any turbine? No. So the shaft work, this one will be 0 because no rotary equipment. Can you see any piston, any expansion, any contraction? No. So this term will be 0 because here we have no expansion, contraction, piston. So what we have here at the end, so this equation will be inlet mass flow rate times specific enthalpy of the inlet plus kinetic energy of the inlet equal mass flow rate of the outlet times specific enthalpy of the outlet plus kinetic energy of the outlet. After we cancel all of these terms, this will be what we have at the end. Again, conservation of mass says the total mass is constant or can be changed. It's constant. Here we don't have generation, we don't have consumption, so the inlet mass flow rate, this will be the same as the outlet mass flow rate. Mass come in, mass come out. They are the same, so this will be cancelled. Here when you analyze any equipment, this is what we need to find, the velocity of the outlet. Okay, so we have three unknowns here. We have enthalpy of the inlet, enthalpy of the outlet, and then we have the velocity of the inlet. So how we can find the enthalpy of the inlet, enthalpy of the outlet?
Steam table.
Steam tables. This example we have steam. So you can go to the steam tables and you can so at the inlet condition we have 0.5 megapascal and the temperature is 400 degrees Celsius. So from the steam table, the enthalpy of the inlet, this one will be 3272.3 kilojoule per kilogram. Again, kilojoule, this is not a SI system. So in order to have a joule, so this one will be 3272.3 times 10 to the power 3 joule per kilogram. And same for the outlets. For the outlet here, we have the pressure is 0.1 megapascal. We have the temperature is 350 degrees Celsius, and then if you go to the appendix, then specific enthalpy of the outlet, this one will be 3157 75.8 times 10 to the power 3 joule per kilogram. So now I have enthalpy of the inlet, enthalpy of the outlet. So I have one information list, which is the inlet velocity, right? In this problem, I don't have any information that I can use to calculate the inlet velocity. Some of the problems, you will find some information. I can give you volumetric flow rate, for example. I can give you the cross-section of the inlet pipe. Then you can use them to calculate the velocity you need. But here we didn't have any information in this example to calculate the inlet velocity. And here we need to understand the function of the nozzle. So if you have a nozzle, so the whole idea of the nozzle that you have like a pipe or something with large cross section, and then you have the nozzle, it's a very small opening at the end of this one. So if you have flow coming here, this flow will go from this inlet, so let's assume this is the inlet velocity, this is inlet diameter, and this will be the outlet. This is your nozzle. So nozzle, it's very small space or very small area that we have, and the flow will move through this very small area. So this is the outlet velocity, this is the outlet diameter. So the diameter of the nozzle is very small. So the diameter of the outlet is smaller than diameter of the inlet. So this means, just by logic, conservation of mass says we have the same mass coming in, the same mass coming out, right? If you have mass coming through this large cross section, and the same amount should exit at this very small cross section, so which velocity will be larger, inlet or outlet velocity? Outlet velocity. Okay. So based on this description here, so the outlet velocity will be larger than the inlet velocity. So because we understand the mechanism that nozzle is working, then we can assume that inlet velocity, which is too small, can be neglected compared to outlet velocity. Because again, outlet velocity is much larger than the inlet velocity. Okay. This is the case that we have in heat in nozzles. This will not be the case in different devices. So each device, you should understand how this device operates. Because for each device, we have some logic assumption that you can assume, you can propose, and this can help you to simplify the equation. Okay. So if we have this one here, then we can say the outlet velocity. So now the outlet velocity squared, this will be 2 times inlet specific enthalpy minus outlet specific enthalpy. So this will be the equation we have here to calculate this one. So if you substitute in this equation, or what we have here, so sub in the equation, then the outlet velocity in this nozzle, so this one will be 439.5 meter per second, and this is what we need to calculate at the end. So this is the principle, how we can use our understanding of conservation of mass. How can we use the mathematical form of the first law of thermodynamics, conservation of energy, to analyze different equipment? Clear?